Or good morning, everyone. So today I will tell you something about Interpolis, the insurance company, and prevention behavior and how these two are related. There is something we would like to know about prevention behavior, and I will introduce that topic to you. And as Chris already told you, we have a data set and we have a question, or actually a couple of questions, and we really hope that you could help us with that and also give us some practical advice about what we should do based on your results. So Interpolis is an insurance company and situated in Tilburg, and we especially have a lot of damage insurances. We have 1.3 million customers who take out damage insurance, and you can think of car insurance, home insurance, travel insurance. And yearly we have about 350,000 damage claims. And we noticed that a lot of those damage claims could have been prevented. For example, this kitchen fire. A lot of the kitchen fires, they start from a grease fire. And well, if they had a fire blanket, this could easily have been prevented, or at least the damage of it could have been reduced. And you can imagine if more people would take preventive measures, or people would take more preventive measures, that a lot of sorrow can be reduced, but also we will get less damage claims, and therefore we could reduce our insurance premium. And that will be beneficial, of course, for Interpolis, but also for society. So therefore, Interpolis is, well, into the topic of prevention, and we really would like to stimulate prevention behavior amongst our customers. When we're talking about home insurance or home content insurance, there are three risks involved, in which there are prevention measures: the risk of fire, the risk of burglary, and the risk of water damage. And if you look at the prevention behaviors, we can distinguish investment behaviors, and that are behaviors that require some financial costs, but only require a one-time action. For example, buying a smoke alarm or buying an alarm system. And you also have curtailment behaviors, and that are behaviors that involve no cost or low cost, but you have to do that more frequently. For example, locking the door every time when you leave the house. So you have to do that always, else it isn't effective. We did some previous research on prevention behavior, and what we saw was that all prevention behaviors fall on a one-dimensional scale. So this implies that people that take out a lot of fire prevention behaviors, they also perform a lot of burglary prevention behaviors. And we also noticed that there was a specific order of these prevention behaviors. So a lot of people have a smoke alarm, a lot of people always lock their doors, but just a few people have an alarm system, or just a few people have a fire extinguisher in their homes. And what we also saw, that there was a transitive ordering in these behaviors. So we refer to this as the prevention pyramid. Which is this. So it means that so a lot of people have a smoke alarm, and less people always clean their gutter, and even less people have fire blankets, and just a few people have an alarm system. But the people that have an alarm system are also most likely to have a fire blanket, to clean their gutters, and have a smoke alarm. So that's a transitive ordering. And we state if you perform a lot of prevention behaviors, you probably have a high attitude towards prevention. You're very prevention minded. So what is interesting is to know why do people perform prevention behaviors or why don't they, and why is that specific order the way it is. So why do a lot of people have a smoke alarm, but just a few people have a fire extinguisher or an alarm system? Well, if you look at literature, they distinguish some factors, some explanatory factors for this. First of all, the perceived vulnerability towards the risk. So how high do you perceive the chance of the risk to be? You can imagine if you live in a neighborhood when there is a lot of burglary, that you perceive the chance of a burglary quite high, and therefore you will always lock your doors and you will have certified locks on your door. Another one is the perceived severity of the risk. So how bad do you think the risk is if it happens to you? The effectivity of prevention behavior. So how effective do you think it is? Do you think it really works, or you think there's another alternative? The financial costs. So how expensive do you think it is? The perceived effort. So how much effort do you have to do to install a smoke alarm or to install an alarm system and also switch the alarm system on every day? And of course you have to be acquainted with the behavior, because if you don't know the behavior, of course you cannot perform it. So for example, if you take the smoke alarm, a lot of people have a smoke alarm and not a lot of people have a fire blanket or a fire extinguisher. So the vulnerability and the severity of the risk is the same, because we're talking about the risk of fire. The financial costs of a smoke alarm and a fire blanket are about the same. And the perceived effort, I would say, is about the same, but I'm not sure. So maybe it is because of the perceived effectivity. So maybe people perceive a smoke alarm to be more effective than a fire blanket. I don't know, but that's something that we are interested in to know. So the questions that we have are, so which factors determine and to what extent whether prevention behavior in general are performed? So then we're talking about the factors that I just mentioned, but you can also imagine that personal characteristics can have an influence. So people, for example, that have a higher income, they might perform more prevention behaviors just because they have more means to. So our alarm system can be quite expensive, so people that have more money, it's easier to afford for them. Or people that live, you have people that rent a home and you have people that own a home. Maybe people that own a home, they would see prevention behaviors more as an investment in their home. For example, the certified locks. So it can also be that the personal factors are a big influence on explaining why people do or do not perform prevention behaviors. So that is actually the second question. Are this mostly personal characteristics or prevention-related characteristics that explain why people perform prevention behavior? And of course, you can also think that these factors different depending on what prevention behaviors we are talking about. I just mentioned the example of the fire blanket versus the smoke alarm. Maybe that's because of the perceived effectivity, but maybe the reason why not a lot of people have an alarm system is not because of the effectivity, but because of the financial cost involved or the effort. So the factors can also depend on the specific behaviors we are talking about. Okay, why do we want to know this? So, as I said, Interpolis tries to influence this prevention behavior. So we want that our customers will perform more prevention behaviors, and also that more customers will perform prevention behaviors. And we do this with several well, several things, activities, especially marketing communication. So you can think about the content, so the message that we're trying to bring across, and that can be through online banners, social media, TV commercials, radio commercials, well, things like that. Targeting, so now we don't have a specific targeting, we just target everyone. We just put it on mass media and everyone is targeted actually, but maybe we should focus on a specific group. Offers. Interpolis also has a prevention shop where you can buy prevention measures as an alarm system, smoke alarm, certified locks. But actually we are not that cheap, so maybe we should think about giving a discount or do other promotional actions if the financial costs are an important factor. Services, okay. If the perceived effort, for example, is very important, is a very important predictor, then maybe we should offer specific services, people that help you with the installation of an alarm system or the certified locks. We don't have that as yet, but that can be an idea. Oh yeah. So now I will show you an online video that we made. It's in Dutch though, so not everyone will. Oh ja, het geluid van niet te
Binnen een paar minuten kan er geen verwarring aanrijden en uitslaan hand met stevige rook. Binnen 3 minuten kan er ook fatale gevolgen hebben. En binnen 1 minuut hang je een rookmelder op. Rookmelders zijn geleverd. Waar mag je nog?
Okay, so this is an example of an online video that we made, and as you can see, the factor that is most central in this video is effort. So it takes hardly no effort to put on a smoke alarm on your ceiling. And also in the voiceover, if you heard it, the severity of a fire is stressed, and also the effectivity of the smoke alarm. Smoke alarms, they save lives. And if you look at the social media content, the banners that we use for that, they're not so much about the effort. They're actually more, well, a mix of vulnerability, severity, and the effectivity. So, for example, if you see the fire from the roof, it stresses, okay, so the chance on a fire is there. It's quite bad if it happens to you, and it's very effective to clean your chimney on time. But there's nothing about the financial costs, for example. If that is the most important factor for people, maybe we should more stress about that. And also the strategy is not very clear. So we have, as you could see in the online video, it was more about the effort, and these are more other factors. So we don't have a really clear strategy on that. Okay, so we did a survey to answer these questions that we have. It was on a consumer panel, and they were all Interpolis customers. 263 people participated in this survey, and we asked some background questions about the person, like age and gender, and also about the home, like ownership of the home, type of home, year of construction. And we asked 53 prevention self-reports. And these are not all in your data set. So the questions were about the investment behaviors and the curtailment behaviors. Here you see two examples of that. So for example, for the investment behavior, do you have a dripping tray for your washing machine? A dripping tray is something that you could put under your washing machine to prevent water damage. Yes, a separate dripping tray. Yes, it was integrated. No, I don't know, not applicable. And curtailment behaviors. Do you lock the doors when you leave the house? Yes, almost always. Sometimes, no, almost never. And then we coded it by nominal. So we give a 1 for a positive answer and a 0 for a negative answer. And it's a missing value if someone doesn't know or it's not applicable. And for the curtailment behaviors, we use the strict rule, and that is, okay, so you only get a 1 if you do it always, and not if you lock the door sometimes, because that's not that effective. So of these 9 behaviors, we asked the perceived vulnerability, the perceived severity, the financial cost, the effort involved, so all the factors that we just discussed. And also we asked if people were familiar with the behavior before the questionnaire. So this data is multi-level and it looks like this. You have 9 rows per person, since every behavior is on a separate rule. And that is because we first want to answer the research question, what factors determine the general prevention behaviors. So therefore we have to cluster all the behaviors. And in the column have it, well, there you will see if someone has the specific prevention behavior, and in total that is prevention behavior in general. So this is the data set that you will work on. Okay, so the assignment. Chris will give you the specific assignment. And so you have to do some analysis, multi-level analysis, and we really like you to interpret your findings and give Interpolis some practical advice based on your results about what we should do. And you can think about the things I mentioned for the marketing communication, so the content, the targeting, but it can also be something else. If you have another idea, we would really like to hear it. Yes, and the assignment is graded, and the best group wins a small prize. So I wish you a lot of good luck with that. And now up to Chris.
Okay, so let me try to take you through what the assignment is and what the data looks like, just to get any misunderstandings out of the way as much as possible. This is what the data set will look like, and you see on the left all the variables that are in there. ID, that's a personal identifier. Then a code there about exactly what the measure is. So number 1, means it's an alarm. Number 2 is inbraakstrips. I didn't remember do you remember what the English term was? I looked it up at some point, but it's the things that you can put on your windows to make, and on your door to make access more complicated for burglars. Then the one that is going to be the target variable. Do you have, or do you do the measure? Have if it's something that you buy, do if it's something that you do, like cleaning your gutters. And then we have some characteristics starting from male all the way up to there, house, year. These are all characteristics of the person. So if you're male, how old you are, what kind of family you have, if you own the house, what the type of the house is, and the year of construction. Okay, some of these obviously are categorical variables, so you have to take that into account when you do your analyses, but all this is ID related, so to speak. So in the 9 rows that you have per person, the values for age will be exactly the same for that person, obviously, because all 9 rows are about the same person. And then you get a couple of other variables over there, starting from costs all the way up to buy, and all these are characteristics of the measures, of the prevention measures. So people have been asked, as you just heard, okay, what do you think an alarm costs? What do you think inbraakstrips costs? How many, what kind of trouble is it to, let's say, buy and install an alarm, I think. How effective do you think an alarm is? How effective do you think it is that you lock your doors, and so on. Then in general also the probability of that particular hazard. So how likely do you think it is that you will experience a burglary or a fire in your house? And this is not one that was asked of the participants in the survey, but this is the difference between, on the one hand, the things that you buy, equal to 1 if yes, and equal to 0 if not, and the things that you do. So I think half of these 9, I don't know, 4 or 5 or so are things that you buy, the other half are things that you do. So that's also something that you could use as a characteristic of the measure. Okay, so that's all that there is in the data. We have 260 or so people in there, times 9 measures per person, so 9 times 260 cases or rows in the data. And it looks like this, as you saw it on the slide, on the top left there. Identifier number 1, 9 rows. Identifier number 2, 9 rows, and so on. Here you see the different measures from 1 to 9. Here you see whether or not somebody does this or has this. First one was a male. Second one was a female. Age is not 11, but 11 is a category in the variable. So this is must be quite a high number, so representing an older person, I think. Level of education, kind of family, and so on. Okay, do realize this is all real data, so we have missings in here, and we may have weird things in the data as well. I think we tried as much as we could to get all the weird stuff out, but it could very well be that as soon as you run your analyses that you find that there are still a couple of weird things going on there. You simply will have to deal with that. You'll see also here that, for instance, there is a missing, and there are more missings, and you have to do something about that as well. If you have variables where there are lots and lots of missings, let's say all the way up to that 20% of your data would be lost if you would include that variable, and you have to think carefully about what to do. And, for the rest, this is just your standard Stata data set. Then let me, just to make sure that nobody goes wrong on question number 1. This is multi-level data, so okay, you don't want to use regress, right? Because the thing that we want to predict is 0, 1, so regression is not a good thing to do. We do not want to use XT regress, so the multi-level variant of regression, because this is not regression. Logit might be an idea. In principle, that would be a good idea if you have a target variable as we have here, that is 0, 1, but it's multi-level, so for this you'll need XT logit. If you remember nothing of today, remember that, because otherwise you'll go wrong on question number 1, and the rest will be hopeless. Okay, so let's see what the assignment looks like. Okay, so I start with briefly mentioning once more what's in there. So this whole first part is all is nothing new. This is all the stuff that is in the data. The data are in long format. We have about 2,400 rows. And here it starts from, well, now we can, for instance, predict, have it from the variable costs and all the other variables that we have. And the initial questions, actually the whole page of initial questions, all the way up to 6, is basically there to get you acquainted with the data. So the first question is, okay, here you need to do something multi-level. Why is that a good idea? Well, you could easily get that from the lectures. The second one is have a careful look at your data. Do you see any weird things or inconsistencies even before you run an analysis? Have a look and deal with it. And in particular, I saw one under 2b. There are 10 persons in the data who do not vary their answers for the different measures. So if you ask them how effective do you think the following measures are, they give the same answer for all 9 measures, which in all likelihood means that they've just, answered this with their eyes closed. And we want to take these out, but you have to be able to find them in the data. So that's one of the questions here as well. Find these 10 and get them out. And a couple of overview tables. Okay, have a look. Which of these measures is occurring most often? Which of these measures is considered most likely? And which of these is considered most severe? And number 6 is actually the first time that you need to run an analysis, or actually 3. Once with all the personal characteristics included, once with all the measurement characteristics included, and once with both sets of variables included. And then you look at your data and try to see, let's say, as a first approach, what's happening in the data. Okay, the the slightly more complicated work starts at question number 7. So now we want to understand a little bit better what's going on with the data. So one of the questions is, what is the size of the effects? If we look at the things that have an effect here, which of these are most important? Which effects are strongest? That's question number 7. 8 and 9 consider transforming different variables and thinking about interaction effects that might be at work here. So all, in principle, nothing new. Do realize that some of the things that we considered in the, in fact, the first lecture, so all these ways to find interaction effects and to find transformations, many of these commands might not work after a multi-level command. So if you typed xtlogit and then do something that is trying to find interaction effects or something else, might be that it doesn't work just because you typed xtlogit before. One way around that would be, okay, for a minute, forget that it's multi-level, type logit, and then do what you are allowed to do. That's good enough. We've seen that a couple times in the wikis as well. And then, let's see, number 10, in the multi-level part, I talked about that, I think, twice already. You can split that in a effect within the persons here and in an effect between the persons. And you have to try to figure out how that works. Are the effects within persons or between persons, and what's the difference? Now, by that time, you've pretty much come up with a decent model, I hope, of what's going on there, and a bit of an idea of what's going on substantially. So we don't want answers of the kind, yeah, I see that X is a significant predictor for Y. You need to have some substance to it. What does that mean? Is it a substantial effect or not? And if it is, then how would that help? So basically, question 11 is, this is crucial. Think, always crucial. Think about what this means. Okay, now we get a better feeling for what's going on. Run additional analyses if you need to. For instance, try to figure out here, are the effects any different for different kinds of measures? And what would that mean? And try to come up with a suggestion, an advice. Okay, given that we now know that it's like this in the data, what should Interpolis do? What would be good advice? Or what shouldn't Interpolis do? Might also be good advice here. The advice should be appropriate in the sense that you should get it from the data. I mean, there are all kinds of things that you could try to advise to Interpolis that might even make sense, but are not based on the data. So, yeah, you know, you can give it as an extra, but it's not what we're aiming for. It has to be based on the data itself, and it needs to be actionable. So think, yeah, you know, think carefully next time you come up with an ad. Yeah, good advice, I guess, but not very actionable. What are we going to do here? And if need be, and I can imagine that there really is a need to, run some additional analyses to figure out what's going on in the data. If you think, I think there is something peculiar going on, then if you can, try to figure out if that really is the case by running an additional analysis or two. Okay, at that point, we're basically done, and I mentioned in the assignment that the emphasis in the evaluation of the whole thing is, in fact, on that page that starts from 7 and then goes up to 11. So the first page is to get you started, basically. The second one is to see what you can do with data. Okay, all of that is just about what the assignment is. I'll get into the logistics in a minute. Any questions about the data set and what is necessary to do here? Very good. Logistics of the whole thing. You can work in groups, and the groups you can form yourself. You can, or you should do that on Canvas. You can self-group, so to speak. Maximum is 5, minimum is 4, otherwise I have to grade a lot. I don't like that. Obviously, answers you write should be your group's answers and not everybody's answers. It has to be written text. Okay, so no very brief yes, X on Y, and that's it. And you have to explain what's going on. It's a story about the data, not just a do file. Nevertheless, I do want to have a do file, and then exactly the do file that you used, in the sense that the data that is now online, or almost online, if I use that data just like you, and I run your do file on that data, it should give me all the things that you have seen and used in your answers. So a good idea would be to put in your do file things like this. The below line generates the regression table for model 1, question who knows what, and then the actual regression, so that I can see from the do file, aha, the answer to question 6 is coming from this analysis over here, instead of just a huge do file where I cannot see very well what's going on. In general, I think it's a good idea to invest some time, so to speak, in making that do file look good for several reasons. The most important one is for you. You're working on this with 5 different persons. You have to make sure that the other people understand what you're doing, and you have to make sure that what you run will run for somebody else as well in an understandable way. So that already suggests that just being able to understand it yourself might not be enough. And the other reason is simply, and it shouldn't be, but that is how it works, if I get a do file that looks good, that already helps. If I have to figure out what are they doing in okay, that it shouldn't perhaps influence the grade you get, but I think it does. Okay, let's see. Yeah, all the things that you do with the data before you run your analysis, such as getting rid of cases or getting rid of variables or of persons, hard code this in the do file. So do not go to the data file and then delete whole rows or columns, and then mention that in the do file. I deleted the command that you use to get rid of data or to change data or whatever you do with the data. Make sure it is in the do file. See. Yeah, then in the end, yeah, this is going to be evaluated, and obviously this is for a large part dependent on the correctness of your answers. And what we will also take into account are these things over there. So the clarity of your do file. This has to be crystal clear what's happening there. Proper and clear argumentation for the decisions you make. So every once in a while you have to, decide. There are only a couple of people in the data with some weird characteristic. This is so weird a group, and they mess up my results. I leave them out. As long as you have a proper argumentation for that, fine. But the argumentation has to be there. Make sure that you have it. Then, well, you shouldn't see the actual questions as necessarily the only things that you have to deliver. Basically, all of this is leading you up to question 11, and question 11 is come up with decent advice. So if you feel that there is something else that you need to do here, extend the analysis in some direction because it's not really clear yet what's going on, do it. So it's not that, I now answered everything up to 10 and then 11, that's it, and now I go home. That's in all likelihood not how it will go. We went through the analysis ourselves a little bit, but not completely. So there might be all kinds of things going on here that we also didn't see just yet. And fourth, of course, the appropriateness and the usefulness of your advice to Interpolis. It has to have some kind of advice in the end that makes sense. Okay, so then, as an extra note over there, this is the kind of thing that we're setting you up to do. At some point, you have something like this. There is a practical problem or an academic problem, doesn't matter very much what it is, but there is data that backs up what the answer might be, and your job is to try to figure out what the answer is. And the answer lies somewhere in the data. What we try to do is make sure that, over the course of 3 of these courses, you're able to get that answer out of it. This is the only thing that we need to know about multilevel, and all these things are, in principle, relatively straightforward extensions of the stuff that we've done before. We will see that in practice, to actually do it, it will be, a bit more nasty. But the principles themselves shouldn't be too complicated. So what we had already was, you may have forgotten, random intercepts. So the point where the graph hits the y-axis, that could be different for different groups. And this was the graph that we had for that before. So if we know here that the same colors are all from the same cluster, so for instance one cluster could be, as in the prevention data, an individual, and we have, let's say, here perceived effectiveness of a measure, and there we have, we have 0, 1 in the prevention data, but let's say how likely it is that you would do it. Then you would expect here perhaps something like this. If this is a person with an upward sloping trend here, this is saying, okay, the more effective you think prevention measures are, the more likely it is that you actually have them, which would make sense. And then you could also find that in the end, if you have all these lines for each and every one of these individuals, very stylized example here, that then the trend across the means of those lines would actually be downward sloping, which would be really weird, but in principle it's possible. This would mean, if I look across individuals, so the individuals who think on average that all measures are relatively effective, actually are the ones who have less of these measures. Wouldn't make any sense to me, but in principle this is a possibility. Okay, so given that we have these lines over there, all these lines have a different intercept, a different place where they hit the y-axis over there. So what we're trying to create is, let's say, a big bunch of these of these straight lines, all with the same slope in this case, but that do vary in terms of where they hit the y-axis. Okay, given that, we can also vary the slopes. We just only varied where they hit the y-axis, and they were all sloped like this. Perhaps there's something to be gained if we allow that to wiggle a little bit. Then we could have more than 2 levels. We now had measurements within persons, but persons could be within groups, and the groups could be within even larger clusters, so you can imagine that there are more than just 2 levels. And we have cross-classification, that is, if you have nesting that is not one in the other, but let's say this group, you are all here in the same class, and you are in different kinds of, let's say, sports clubs. So there is clustering of different kinds, but the clustering is not nested within each other. That makes matters slightly more complicated. So we'll go through what to do if you want to do this. And the first thing that we'll find out is that we need a different command for that. It would be nice if that xtreg and xtlogit would work with all of these two, but it doesn't. So we need something else. Okay, first thing, random slopes. So here we're sort of sticking to each and every one of these lines has the same slope. And what we would like to know is that a decent assumption, or is there any evidence that the fit with the data would be any better if we allow these to have each of them have a different slope. Okay, let's see. This was the technical background that we sort of had before. This is one x as an example and a y, and we have that C0 value, the intercept. And what we actually tried to do was, well, we make different intercepts for different clusters. So we have, instead of that C0, we now have a C0 plus separate dummies for each and every cluster that we have in the data. So you could say that these D2s and DKs over there represent what you should add to C0 to make sure that you get exactly the line that you want. So the different heights of these lines are exactly what you find in these dummies over there. I have to peek for a minute, yeah. Then we said, well, yeah, you could do it, but in principle it might not be such a good idea because you could have a big bunch of clusters over here and you might be forced there to include 100 or so dummies, one for each and every cluster, which would end up being a big mess. So we tried to sort of summarize that in just a single Greek letter over there, usually called delta. So that's shorthand for all these dummies over there. All these dummies over there get different coefficients. We can average out these coefficients, and then let's say that average is 3.5. That 3.5 we can put in the C0. Okay, so now we have variance around C0 plus that 3.5, and we hope that that variance sort of looks like this, and there's nothing else than hope. Very often this is pretty much okay, but this is a true assumption here that you in principle could actually be willing to test. But the big thing here is, here we might need to estimate 100 separate dummies. Here we reduce this to just one variable that we have left, and the only thing that we estimate from this is the variance around 0. So it's an efficient way to estimate the whole thing. Okay, why do I repeat this? Well, this is starting from C0, adding, well, what if every cluster would have its own C0, and then abbreviating that to, okay, C0 plus a Greek letter. That's one way to summarize what's going on there. Well, if I can do this for C0, I can do it for all the other C's as well. So if I want to make an issue of the fact that this C1 over there might vary for the different clusters, in principle I can do the same thing, and that's exactly what will happen. So here we see, this is where we left off. We have different intercepts for the different clusters. Do we have that? Yeah. Now I'm looking at the C1 over there. I'm thinking, well, that C1, that slope, might be different for each and every one of the clusters. So now I'm creating different slopes for each and every one of the clusters in the data. Okay, now I again get that same problem. This might be 100 extra coefficients to be estimated. And in fact, if I would have left all the dummies over there, then I might have 200 extra coefficients to be estimated. So I do the same thing here. I try to summarize this in, well, the original C1 plus some noise around that C1, because there are different slope values for different clusters. Okay, so what I would hope to be able to find there is, well, usually this is, what is that? How is my Greek again? Is that a zeta? Yeah, I think so. So this is estimating, let's say, how wild the slopes are varying across the different clusters. So if that zeta value there is very small, that would mean, okay, it's like this and with just a little bit of wiggling around it, not enough to be bothered about. If that zeta there is very large, then this is suggesting, okay, so apparently the slopes of all these different clusters completely varies across the different clusters, and that will tell us something about how good our approximation was by just assuming that we had a single C1 for each and every one of the clusters. Okay, so basically, technically the same thing. First we had an intercept that we make a bit of a fuss about, and then we do the same thing for that C1 for the slope. Okay, then we need something else. XT-reg doesn't work, and mixed in fact does. Actually that whole XT-reg is obsolete Stata, so according to Stata you're supposed to run mixed for everything. And the issue is that mixed has a slightly different way of different kind of command, looks differently. Here you have it. This is what we saw before, xt set, and then you have to define, okay, what are the clusters in my data? So, you know, classes or person IDs or what have you. And then you run your regression just as you normally would. The only thing that's different is you type xt in front of it. You see something here that is relatively rare in Stata, perhaps also one of the reasons why they got rid of it. And that is that, yeah, for this, you need to know that. And this is also why it is a good idea if you have a large do file with a couple of these xtreg commands in it, just to make sure, repeat the xtset command right above it. Because otherwise, Stata will try to look back, okay, what is the last xtset that I saw? And you must simply hope that it finds the right one. So it's a good idea to keep them close together in general. However, for the mixed command, you have to type that same cluster variable in the actual line. So there is no 2 lines of code. There's just a single line of code. You type mixed y x1 or x2, x3, and so on, however many you have. 2 of these vertical things. On my keyboard, they are all the way, let's see. Are these, yeah, on the right. Then a space, and then you type your cluster variable with a semicolon behind it. Okay, so that is almost equivalent. And I'll show you in a minute that it's not exactly equivalent, and I can also tell you a little bit about why it's not exactly equivalent, but that's the whole idea to change it like this. And here you see one example. Here what is this? Daniel's data. Doesn't matter so much exactly what it is, but here you see an xtset. I'm defining the person identifier there. I run my xt regression on the variable increase, and I get a row value in the end of 0.19, suggesting that 19% of the variance is at the individual level, and the rest is at the measurement level. So 19.4%, let's try to remember that. And here you see it the same thing, but now through that mixed command. Mixed, increased, and 2 of these vertical things, and ID, and a semicolon. The first thing to note is that, well, here, there is no iteration log. You get your answer immediately. There, you do get an iteration log. So apparently here, what's being used is log likelihood, which is different from what was done there. Here, this is a closed formula. So if you have data that's really large, then typically this will be faster than that. So as long as the analyses are more or less the same, it might be a good idea to use the other one, not the mixed one. This, if you have a very big data set, may not converge or may take a very long time to converge. So that's also something to realize. This can happen. And in the end, you get, well, something that is, well, similar, but not exactly. What was so nice here was that the row value over there, this is actually calculated based on these 2. And here, Stata is not so friendly to give you that row value anymore, and you have to calculate it by hand yourself. And the way to do it would be, well, exactly the same in principle. Here you see it, 11.599, that's there, over 11.599 plus 50, here 18.6. So that's close to the 19.4 that we had before, but it's not exactly the same value. So you might get something that is slightly different here. And the reason is, well, although we're optimizing more or less the same problem here, we do it in a slightly different way. And whereas in standard regression, forget the multi-level, just the normal regression that you know from the second methods course, there, if we would have done likelihood estimation, we would have gotten exactly the same results as for standard regression that we normally do. Here, it's slightly different, but luckily the differences are slight, usually. So we need not worry too much about this. But it does ask for that you calculate the actual row value by hand. Okay, the convenience of this whole command is that as soon as you have this, you can start saying something about where you want the actual randomness to be. If you do that, we just saw on the previous slide, you're just saying, okay, I want my random intercept, that's C0, that is allowed to vary across the different groups. Here you can make a list in principle as long as you want, but I suggest doing this one at a time, for each variable where you want to have a random slope, or want to test whether a random slope makes sense. Okay, here you have only one x1, so the only thing that you can put there is x1. You can have a longer list of predictive variables over there, let's say x1 through x10, and then choose 1 or 2 over there. My suggestion would be, do not just plonk everything in there, because this is a nasty thing to estimate, and if you have 10 of these random coefficients, random slopes over there, in all likelihood the whole thing will not converge. And in any case, the output will not be very instructive for you. So my suggestion would be go with these one at a time to see if it makes a difference. Okay, so let's see. Here we have it. Same data from Daniel. Now I included happy manipulation, baseline, and order. Let's see, what was that again? Daniel's data was we're measuring heart rates by phone, and we asked people to remember either something where you were happy or where you were angry. Happy manipulation is equal to 1 if it was the happiness case. The 0 case is where you were angry. Baseline is your baseline heart rate, and order is whether you got the happy manipulation first or the other one first. Okay, so all these might do something. In this case, the variable that identified the subject is labeled subject ID. I'm telling here, okay, happy manipulation, that's that one over there. Let's check that to see if there's any evidence for a random slope. First, you see again that log likelihood part, and here you see, well, this went well. Stata mentions I'm reaching a place on the surface that I'm trying to optimize that is not concave. You can imagine if it would be, if it's something that's bollig naar boven in Dutch, then if you keep walking upwards, then at some point you're going to reach the real maximum. And it's obvious if you know that the whole surface has that shape. If there are dents in there every once in a while, then it's not that obvious anymore that, well, first of all, that you will arrive at any kind of maximum. And it's not that obvious anymore that you will arrive at the absolute maximum. It might be that, that you are in a local maximum somewhere, even though somewhere else there was a very large summit that you now missed. Stata realizes at some point, whoa, I'm in a place where there are dents. This is nasty, so let's try to backtrack a little bit and start again until I find, let's say, at least a part of that surface that is concave all the time. In this case, it happened twice. And then it found, let's say, a spot there where it had the idea, this is improving in the right direction. And then in the end it converged to this here. Let's see, we have the happy manipulation over there with a coefficient of -3. Here a bit larger, it's also significant. So this is saying, okay, the increase in heart rate that you have here is smaller when you recall something that was a happy memory than when it was an angry memory. Or stated the other way around, angry memories increase your heart rate more. And it is highly significant, so this is suggestive of the fact, yeah, there is a difference between these two manipulations. Now, do I have that? Yeah, and this is the same thing as what I had there, but because it was so small, I increased it over here. So now we get an extra term over there. This one we had before. That one we also had before, when the model was still empty. All this whole random effects parameter stuff is referring to, let's say, a Greek letter in the formulas that I showed you before. That residual over there, that's the epsilon that we start with in any kind of model. There is a residual somewhere on the right, and that's the one at the bottom over there. That var cons that you see over there, that's that delta thing, the random intercept that we started with when we used xtreg. And this one is the variance, that's the zeta that we had before. This is checking, okay, to what extent is there any variance in that slope? And in this case, well, we see a couple things here. First, yeah, this is 0. Okay, 10 raised to the power of -13. For all practical purposes, this is really 0. So it looks like there is not a lot of evidence here that from the, what was it, the -3 slope, I should say like this. So the downward slope that we have, yeah, there is wiggle room and it varies with 0, so it's kind of like this. Okay, so there is not a lot of evidence, or no evidence at all actually here, that these slopes are different across different individuals. So that's the first comparison you should make. This number over there with that number over there. If this one is large compared to that one, that is saying, well, if this is the variance around that number, let's say that here you would see 100, then the variance is 100. So the standard deviation, that's the square root of that variance, would be 10. So that would mean this coefficient there, in principle, runs roughly between -3 minus 2 times 10 and -3 plus 2 times 10. So basically varies between very negative and very positive. So the line is doing this across the individuals all the time, suggesting that there is a random slope there. And the other way to see if there is something that is of interest is by comparing the numbers that you see over there. So one way to do the calculation would simply be you add all these up, that you put in the denominator of the fraction, and this you put in the numerator above the line, saying in this case, well, 0 over 0 plus 10.5 plus 45. So the part of the variance that is at this level, I mean, easily seen from these numbers, is close to 0. So apparently not necessary at all to think about random slopes here. This random slope is simply not there. Get rid of it. And you could try to do the same thing with other predictor variables that you have to see if there is any evidence for an actual random slope. Let's see, yeah. Any questions about this, the random slope part? All right, 2 other things to go. Oh, yeah.
So at what point does it say not concave? Because I didn't get that quite clear.
What Stata is trying to do behind the scenes is, let's say, find the highest point in a larger area. Let's say the way to think about it is a blind man trying to find the highest point in an area. So otherwise it would be easy. I'm standing here, the highest point is over there. But you can only see very close nearby. And Stata is trying to feel around where the whole surface is going up. And as long as this is going fine, Stata won't complain and will keep iterating and, let's say, get closer to what the optimal solution actually is. If Stata feels, okay, listen, in a bumpy area where it's not so obvious anymore that my standard optimization routine will actually work, it tries to backtrack in and of itself. There's no need for you to do anything until it finds, let's say, a place in the whole surface where it's relatively smooth again, and then keeps running the whole optimization routine. Every once in a while you might see backed up. So if it really gets stuck and tries to improve and finds itself, this is not working a couple times, then it will simply back up a couple of iterations here and then try a different direction. But by and large, if Stata gets stuck there, the first thing to do would be check your data, because if you have data, for instance, that are highly collinear, so you have predictor variables that are, let's say, very much the same, this is difficult to optimize, and then these kind of things might happen. So that's normally the first thing that you need to do. And if you really get stuck, there are ways to tell Stata to optimize differently. So there is a standard way that is being used, and if you find that that's not working, you can ask for a different kind of algorithm to be used. But well, as soon as you're there, then ask for help from somebody who knows what he or she is doing.
So are there assumptions that you can check always when you do this?
What do you mean assumptions? What kind?
Like for the collinearity part, for example?
No, I mean in general. Even when you do not have any kind of optimization of this sort, it's a good idea to look at multicollinearity between your predictors. So if you have predictors that are highly collinear, it typically is a difficult estimation problem. So you want to check for that. And other than that, there are a couple of papers that show if you have data of this kind with this kind of procedure, then you're certain that the space that you're optimizing is concave. That's sort of a theoretical result that you're good to go. But for all practical purposes, you just run the command and you keep your fingers crossed and hope for the best. And if it doesn't converge, this might be indicative of that either the data that you have is nasty, lots of collinearity in there, lots of dependencies in the data, and then there's basically nothing that you can do. Even if you use other kinds of algorithms, then it's simply because of the data that you have. Okay, then, well, more than 2 levels. The example here is, okay, I have measurements within pupils in a class, within classes, within schools, within districts, within countries. All of that could happen, and if you are into educational research, then this is typically what people really do. I think in our case it will not happen that often that we have 4 levels, but 3 might actually happen. And when you have 3, then in principle you can do, again, exactly the same thing. Let's see how that goes. We already had this, so that delta over there, that was due to different intercepts that we had for each and every cluster. That gave us the delta varying by cluster. And if there is another larger cluster over that, so we have pupils within classes, classes within schools, might be that these schools are cluster levels as well. And that in principle, I not only want to have separate dummies for classes, but also separate dummies for the schools. Again, I now skip one part where I say, yeah, I could want different dummies over here, but I don't want to have it because I then have to estimate too many dummies. This will give me another Greek letter over there, now tau, where this is varying now over the larger cluster. So this was varying over the classes, let's say, then that is varying over the schools. So I have another Greek letter there where I think, okay, there might be different intercepts due to the fact that I have different classes over there. And there might also be different intercepts that are due to the fact that I have different schools over there. Any level that is larger than the class level. So that, again, gives me a Greek letter over there. And the way to estimate it in mixed is, well, easy on the one hand, but treacherous on the other. What you do is you type it like this. Mixed y, x1, 2 of these vertical slashes, school, and a semicolon, more of these vertical slashes, and then class with a semicolon. In this case, obviously, the school level is larger than the class level. Classes are embedded in schools, and it has to be that way. One of the nasty things of this command is if you type it the other way around, yeah, it would be nice if Stata would say, this is not how I would like this, because the larger one needs to be on the left, but it doesn't. It just calculates something else, not exactly sure what. So in the output, you will not realize that what you did is the wrong thing, and you have to make sure yourself that the bigger one's on the left. And then, in principle, everything is exactly the same as what we saw before. So one example here, in the wiki data that we have online, I'm not sure if I have it completely online already, but this is data from sort of funda for motorcycles, so to speak. And there you have nested cases. So one row in the data would be one motorcycle being sold for, or with an asking price, I should say, of a certain height. And we have motorcycles who are of the same types. So all these are, what's that? This is a BMW R1200 GS. And there are more than one in the data, let's say 25 or so. So they are nested. There are characteristics of that motorcycle that determine the price. And these are nested within the larger set of BMW motorcycles. BMW motorcycles might have their own characteristics that may cause them to have different kinds of intercepts. And if you run your analysis, then you typically get this back here. I typed mixed, the price, that's the asking price, the target variable that I have there. Then brand, such as BMW, and then type, such as R1200. And then you get back exactly the same thing. More of these variance components. All these that you see over there are related to, let's say, a Greek letter in the formula. Again, the original residual, that's the epsilon over there. This is for type, and this is for the brand. And you can see here an estimate of the variance at these different levels. So in this case, there is really evidence for random intercepts at the different levels, because here you see that, 10 out of the in total 15 or so is at the level of the type. So there is clustering, and the largest part of the clustering is happening at this level, at the level of the type, and not at that level, the level of the brand. And that you can see from, this is only 2.25 from the total 15 that we have. Okay, so if I want to try to come up with predictors that do a good job over here, it's a good idea to try to find a couple at the level of the type of motorcycle that I have. Okay, makes it a bit more complicated because you get an extra level in there. In principle, you could keep extending this. I don't know what I do not easily see what a larger level than this would be that would supersede it. But in principle, the only thing that you get is an extra row here for that extra level that you added. You could have done this with only type, you could have done this with only brand, but given that they are nested, you can do them both, and you get this. Okay, again, the row value you have to calculate yourself by hand, but it's easily done, so not that complicated. Okay, last one, and the most complicated one, and unfortunately also the one that occurs most often if you have more than just a single cluster level. That is called cross-classification. That is where you have clusters in the data, but these clusters are not nested. So pupils within classes within schools, each and every one is nested in the next one. Motorcycles within types of motorcycles within brands, each is nested within the other one. But if you have pupils within classes and pupils within sports clubs, and you think that that is an issue for whatever it is that you're predicting, then these two obviously need not be nested. So we have two cluster levels playing a role at the same time, but no nesting. It's called cross-classified multi-level models, and this is a nasty thing to estimate. So one thing that will typically happen is that if you think you have this in the data and you do it, then chances are quite serious that you will run into, or that Stata will run into trouble, and therefore that you will run into trouble, so it won't converge or converge to something very weird. And you can see this also from the fact that the command itself is slightly different. Well, more than slightly, I would say. This is if I have two nested levels. Here the example is school and club, that are not nested among themselves. So the students are nested within schools and the students within clubs, but clubs not within schools, nor the other way around. You type it like this, we recognize these vertical things, and the thing to do for a cross-classified model is to put that over there twice, and then the cluster levels behind it. Okay, this is complicated stuff also in the sense that what you get back from Stata is not that obvious anymore. We could try how that works in the data from the motorcycles, because there you could argue these motorcycles are nested within type and brand, but perhaps also within dealerships. These dealerships are not necessarily nested within brands, so this is a typical example of a cross-classified model. This is the basic option where we have random intercepts for these different clusters, so the C0 is varying. In principle, you could also have here that not only the C0s, but also the C1s vary, but this becomes nasty very, very fast. So at this point, there's not so much reason to worry about this. But in principle, all these are possible. Yeah?
Do you still have to put the biggest cluster on the left?
Yes. Yeah, there is, I'm not sure if I have it online, but there is a technical supplement explaining why this is working. And this is because the whole mix command was actually built up in such a way that you could do all kinds of multi-level analysis with that mixed command. You know, random intercepts, random slopes, and so on. And the random intercepts was actually way below on the list, also because it is quite complicated. So what they show at some point, I have to look if I still have it somewhere, is that by typing it this way, you are able to estimate that cross-classified model with the mixed command. Yeah, but it does involve quite a bit of complicated hand waving and formulas and so on. So it's, you know, in a way you would hope that, let's say in the next version, they would come up with a command that is a bit more intuitive than this one. Yeah, then of course, what we did before, when we just used that XT-reg, we could split up variables in variance within the clusters and between. And as soon as you have more than one cluster, all this can still work, but gets complicated really, really fast. Because if I have a variation within and between clusters, and I have more than one cluster, then I can do this for all the clusters that I have. So we could try to see, is there an effect within classes? And is there an effect within schools? Is there an effect between schools, between classes? Well, very fast, this starts becoming very tedious and very complicated to actually tease out which is which. So if you can avoid it, please do. But in principle, all these are possible. But you have to take very tediously into account which of these levels am I now taking. Is this within cluster level 1? Is this within cluster level 2? Complicated stuff, but in principle, doable. Yeah, then, as I already suggested, this is a command that is, well, nasty in the sense that you can have quite a few things here that can go wrong pretty easily. So very often I've mentioned, okay, this is log likelihood and it can go wrong, and then usually it doesn't for the relatively small size data sets that we have. For this mix command, this can, even with the relatively small data sets that we have, go wrong very fast. The more complicated you make the model, the more likely it is that you'll end up in trouble. So trouble might be it doesn't converge. Trouble might be it converges but to the wrong values. This is typically hard to tell. You get an answer and you think, well, Stata came up with an answer, so who am I to doubt that? If you feel, because you have plowed around with the model quite a bit and have had trouble estimating the whole thing a couple of times, this is already sort of suspicious, my data is weird, then one thing you would be able to do is tell Stata to start with different starting values. There is a default starting value that Stata will take, and it starts from that and then tries to optimize the whole thing. Well, one way to make sure that you have the right solution in the end is force Stata to start with on a different starting point. Then still you're not sure, but at least it's a bit more certain. And then there are different algorithms in the iterative process that you can put on and off. And this is another way to figure out if the whole thing is converging to the right place. It's better if you use 2 or 3 different kinds of methods and all of them converge to the same answer, or almost the same answer. These are your weapons of choice, or the easy ones at least. The option MLE, maximum likelihood estimation. Actually what is going on behind the scenes by default is slightly different from that. It's restricted maximum likelihood. Let's not go there, but this is another way to run the same model. So if you type mixed and then in the end MLE, it will do something slightly different, and you can check if it then converges, even though it didn't before, or if it converges to the same thing. And I think the more powerful one of the two is, well, these extra clusters give you, well, let's say in terms of the formulas, extra Greek letters about which you need to estimate something. So these Greek letters are things, okay, this is a distribution around 0 for each and every one of these Greek letters. And by definition, no, not by definition, by default, we assume that there is no relation between these Greek letters. So that delta that we had and that, what was it, zeta and the tau, we assume all these are not correlated. Well, that's quite a restrictive assumption and might cause you to run into one of these issues over there. And you can let that go by allowing covariance unstructured. So this is saying, okay, you might have a tau and a zeta and a delta, and let's assume that these are correlated, and let's estimate that correlation by hand as well. This sort of frees up the problem with an extra couple degrees of freedom, and it might cause your algorithm to now converge where first it did not. And then still, you know, especially if you have a lot of predictor variables and a lot of random slopes in there, might very well be that this simply won't converge at all.